Consider the differential equation dy by dx equals y squared over x minus 1. The slope field that differential equation generates is off to the right here. Part A asks, sketch the particular solution of y equals f of x through 2, -1. So 2, -1 I've kind of highlighted here. And through that point, we're going to follow the slope field lines, and it looks like it kind of goes up like this and follows an asymptote here. Okay, and it looks like it's kind of going down like this, and it looks like there might be some asymptote down there as well. Okay, so there's my approximated solution through that particular point. And part B asks, write the equation of the tangent line at that point and use the tangent line to approximate f of 2.1. So what I want to do is I want to come up with the equation of the tangent line that goes through that coordinate. Okay, so I want to find the equation of that line. So first thing is I want to find the slope. So the slope, dy by dx at 2, -1, I'm just going to plug it directly into my differential equation. So -1 squared over 2 minus 1, which is 1, and that gives me a slope of 1. And it looks like that tangent line I've drawn there is approximately 1, so that looks about right. So the equation of that tangent line is going to be y equals, I'm going to use a slope of 1, x minus, I want to put my coordinate in, so 2 and -1 is my x and y coordinate. So it's just going to simplify that. Y equals x minus 2 minus 1. So plugging that in, so f of 2.1 is going to be approximated by that y equation at 2.1, and that's going to give me 0.1 minus 1, or -0.9 is going to be the y coordinate. So if I kind of zoom in there, yeah, that looks about right at about 2.1. It's going up a little bit past the -1 value for y. So there's my approximation. For part C, it says solve for the particular solution y equals f of x to the differential equation with the initial condition 2, -1. So I'm going to separate and integrate this expression. So my dy's I'm going to keep with my y. So dy over, and put the y squared in the denominator. So I'm going to separate this algebraically with times and divide. And then the dx is going to come up on this side. And it's all over x minus 1. Okay, so that's the first step. I'm going to separate those variables, the y's with the dy's, x's with dx's. I'm going to integrate both sides. So integrating 1 over y squared, it's integrating negative y to the power, 2 to the power negative, y to the power -2. So that becomes -1, which is 1 over y. But because I have that negative power, I need to divide by -1. So I'm going to end up with a negative on that y. On the right-hand side, it is the special one where we have power 1 in the denominator. That is not a power rule. We're going to use log to anti-differentiate that. So we get log of x minus 1, and then don't forget the plus c. So at this point, I'm just going to plug in my x and y values and solve for plus c. So I end up with -1, -1 over y equals -1. And that's going to be equal to log of, I'm going to plug in my 2, x is 2, and then solve for c. So I end up with 1 is equal to log of 1 is 0 plus c, so c is equal to 1. So when I solve for this, I'm going to plug it back into my equation here. 1 over y is equal to log of x minus 1 plus 1, and then algebraically rearranging this, I'm going to end up with negative 1 over log x minus 1 plus 1 in the denominator. And that's going to be equal to my y. So that represents the specific solution that passes through that coordinate. So when I graph that point, so when I graph this equation, I'm going to end up with that red line which I sketched in there. Now in this case, it looks like there's probably some parts of it on the left. It looks like there's a vertical asymptote maybe through here. Okay, so then there are likely parts of the graph on the left of that asymptote.